हॅलो.
येस
हा
सर.
सर.
करतो सुरू मला वाटते.
ठीक आहे, चालेल सर. ओके.
पहिली स्लाइड दिसते का?
येस सर.
Okay. Good afternoon to all my students. Actually, this lecture was scheduled in one of the lectures of pre-PhD course of Department of Physics, and later on it was scheduled in the pre-PhD course of Nanoscience and Nanotechnology. But what I thought, I should interact with the students uh, in online mode, and I should uh, tell more about the transmission electron microscopy. This is the facility which we are soon installing in the Common Facility Center of Shivaji University, Kolhapur. I have already taken a few lectures on the analytical techniques so far as material characterization is concerned. But today is the important topic, transmission electron microscopy. Its short form acronym is TEM. Sometimes students they misguide or jumble between the word transmission and tunneling, because for tunneling electron microscopy or for TEM only name is transmission electron microscopy, but in AFM we have tunneling electron microscopy mode as well. But I'm going to talk on transmission electron microscopy, and for this I have used the book by Transmission Electron Microscopy Part 1 Basics, second edition book by Williams and Carter, and it is a very nice book, and those who are really interested in learning the electron microscopy, particularly transmission electron microscopy and other aspects of this transmission electron microscopy, they can go through this book, and it is a very nice book. Students, they may ask the questions, they can be in touch with me so far as this topic is concerned via email kyr_phy@unishivaji.ac.in as well. So let us begin our topic by giving scale of structure organization, where I have shown the logarithmic graph of the size of the matter from 10 meter to less than 0.1 nanometer. So this journey of some 12 orders of magnitude of the size, it starts from few assemblies to subatomic particles. So in order to really see, observe, visualize these matters, you need different type of tools or techniques. For example, with the help of naked eye, we can see the material having the size of the order of say 100 micrometer or so, 10 micrometers or so, but roughly 100 micrometers or so. If you want to see the object whose size is less than 100 micrometers, you need to go to optical microscope, where optical lenses are used, and magnified image of the material is seen. But we know there are certain limitations so far as resolving power of the microscopes are concerned. Therefore, you cannot see the object having say the size 10 nanometer or 100 nanometer or so, and for that you need to use X-ray diffraction studies. And there you cannot directly see a matter, but you need to see it indirectly based upon the calculations and interpretations from the X-ray diffraction analysis. Further, you need a CM scanning electron microscope, where you go up to 10 nanometer or so. And beyond that, if you want to see a matter, then you really need another technique. And the technique which I am going to cover today, this TEM, scanning transmission electron microscopy, etc., etc. So object of the size 1 nanometer or so can be realized, can be observed. And beyond that, there are other methods. Particle accelerator is there, but my attention would be will focus on the TEM, where the atoms can be seen. So this is the scale of structure organization. Before proceeding, let us see, let us revisit this slide. I have already discussed this slide when I discussed the scanning electron microscopy. So imaging with electrons, difference between light microscope and electron microscope. We know in order to see the magnified image of the object with the help of electromagnetic radiation, that is visible radiation, you use light microscope where we use photons. Photon, they collide or they incident on the matter, and we see reflected rays, electromagnetic radiation, and we form an image on our retina, and we see the object with the help of photon and light microscope. But if the size of the constituents, if it is less than the resolving power of this microscope, then you need some other microscope called as electron microscope. Particularly these electron microscope, they use instead of photons, electrons for formation of image. Keep in mind, the image is formed with the help of electron microscope. Particularly, there are two types of electron microscope: scanning electron microscope and transmission electron microscope. So the images formed with the help of electron microscope, they are black and white. While the images which we observe with the help of light microscope, they are real images. We can see colored images. So this is basic difference between these two. Of course, you can create colored micrographs based upon some input or algorithm, but you cannot directly or as it is, you cannot see the object with the help of electron microscope. What after all these electron microscopes they use? They use electrons instead of photons, and the glass lenses in the optical microscope, they are replaced by the electromagnetic and electrostatic lenses. And these highly energetic electron beams, they are used for examination of the object on very fine scale. And we have very high resolution at high magnification. We can study structural characterization, we can do the micro analysis as well. So far as magnification and resolution is concerned, magnification is the number of times the image can be magnified, the object can be magnified. So with the help of optical microscope, the magnification is of the order of 1400, for example, and resolution is 0.2 millimeter. While in case of a scanning electron microscope, the magnification is of the order of 2 million and resolution is of the order of 0.5 nanometer. I am giving just orders roughly here and there. Correction factor would be there, but with the help of SEM we can go up to 2 million magnification. But with the help of TEM, transmission electron microscopy, we can go up to 0.05 nanometer and magnification can be 50 million. With the help of this transmission electron microscopy particularly, I have covered this scanning electron microscopy in my earlier lecture. With the help of transmission electron microscopy, you can study the uh, atomic arrangement, grain arrangement, we can study the diffraction, you can know the crystalline structure, you can directly see with the help of bright field and dark field images the grains and the object. You can see biological objects also with the help of this electron microscope. So before proceeding further, once again revisit the slide where I have given the difference between SEM and TEM. Here in SEM, the type of electron which we examine are the scattered electron, particularly backscattered electron, secondary electrons. But in case of transmission electron microscopy, TEM, transmission electrons are examined. The energy of the high tension or the accelerated electrons electrons are accelerated up to say 30 keV or 50 keV or so in case of SEM, while in case of TEM, you can go up to few thousand keV. I'm going to tell you different types of TEM soon. But typically in general purpose TEM, the acceleration voltage is of the order of 300 kV. Specimen thickness, because this SEM, it doesn't need the transmitted signal, therefore thickness is not the issue for SEM. But in case of TEM, typical thickness is say 150 nanometer, 100 nanometer you can say. But with the help of high voltage transmission electron microscopy, you can see the object where the thickness is even greater than 150 nanometer. With the help of scanning electron microscope, where the raster scanning, linear scanning and raster scanning is used, formation of 3D image of the surface is possible. But in case of TEM, as the electron they transmit the matter, then whatever there is in their path, there would be no electron. If there is nothing in the path, the electrons would be there. So in this way, you get a projection image, two-dimensional projection image, so far as TEM is concerned. As I said, maximum magnification of the order of 2000 K, and in case of TEM, it is 5 crore times. Maximum field of view is large in case of SEM, and in case of TEM it is very small because you need greater magnification. Spatial resolution, as I said, 0.5 nanometer in case of SEM, in case of TEM of the order of few picometer. How image is formed in SEM? In SEM, electrons are captured and counted by some counter with respect to position, and correspondingly indirect image is created on the PC screen. While in case of TEM, the direct imaging on the fluorescent screen or PC screen with a charge coupled device CCD type of camera can be done in case of TEM. For SEM, little or meager sample preparation, very easy sample preparation can be done. But in case of TEM, you need laborious sample preparation, and trained users are required in case of TEM. This is the table where it is the list of analytical techniques used in the material characterization, starting from surface structure, morphology, composition, depth profile, etc. etc. So what primary beam is used for interaction of with material, it decides the type of the technique. Here we have electron, ion, photon. But the today's technique which I am going to explain, TEM, STM, EELS for example, the electron beam having energy 100 to 400 keV is used, and the secondary signal also is electron, transmitted electron particularly. In case of EDAX, X-rays are there. So TEM, STEM and electron energy loss spectroscopy, EELS. So these are the topics, and in addition to this, HRTEM. So these are the topics which I am going to explain today. It will take maybe more than 1.5 hours. So all the students are requested to be patient. If somehow if they are not able to listen whole lecture, I am going to put this lecture on my YouTube channel. You can subscribe and you can see other lectures also. But be patient for 1.5 hours. So let us begin our discussion with the historical development so far as research and discovery of the transmission electron microscopy, this electron microscopy is concerned. So first TEM was demonstrated by Max Knoll and Raska. We know Raska is a Nobel laureate who got Nobel Prize for the discovery of TEM. So in 1931, they discovered first TEM. Later on, Raska in 1933, they developed TEM with resolution greater than optical microscope. Earlier microscope, his resolution was not higher than the optical microscope. First commercial TEM was developed by Siemens company in 1939. And in 1986, when the discovery of STM was made by other scientists, Bing and Rohrer. So in 1986, Royal Swedish Academy awarded the Nobel Prize in Physics for the development of TEM to these three scientists, Ruska, Binning and Rohrer. And half amount was given to Ruska and remaining half was contributed, divided into Binning and Rohrer. Later on, in 2008, Jenik Meyer, they visualized carbon, hydrogen atoms and single layer of graphene, and their work was published in Nature in 2008. So these are some of the historical development so far as study of TEM is concerned. This is the photograph of the first practical TEM. This was originally installed in Parben, Warke, and now this is on the display at the Dutch Museum in Munich, Germany. Let us see different forms of the basic TEM. We have high voltage electron microscope. High voltage meaning thereby the acceleration voltage between anode and between the sample and the electron gun. It is of the order of 500 to 3000 kV, kilovolt. Why such a very high voltage of acceleration of the electron is needed? It increases the resolving power of your instrument. Even thicker sample are there, then the electron they can be easily transmitted because they carry tremendous amount of energy, 300 keV, and aberration of the lenses can be decreased with the help of high voltage. But of course, this type or this type of TEM, it has got its own disadvantage also. So these are special purpose TEMs. We have intermediate voltage electron microscope as well, where the acceleration voltage is between 200 to 500 keV. These are called as in situ transmission electron microscopy, where we can irradiate the material in situ, and you can see the effect of irradiation of material and the changes in the images on the atomic structure level, defect structure formation. So with the help of IVEM, where the acceleration voltage is between 200 to 500 kV, you can do in situ TEM. We have ordinary TEM, where the acceleration voltage is of the order of 100 to say 200 kV. Of course, there is an overlap of the acceleration voltage between intermediate and ordinary TEM. We have scanning transmission electron microscopy also. So scanning transmission electron microscopy is nothing but it is the sum of SEM and TEM. So in TEM we know the sample is fixed and the electron beam is illuminated on the sample and the transmitted electron they are recorded. There is no provision of raster scanning of the electron over the sample surface in TEM. But in SEM we can rasterly scan the electron beam over the surface of the sample. So when these two raster scanning in TEM is used, it is called as STEM. We have HRTEM also, and I am going to give much attention to this topic because it is a separate lecture. HRTEM itself is a separate lecture. So high resolution transmission electron microscopy, with the help of this we can achieve, you can see atoms, you can see the what you can say atomic layers and interplane spacing and whatnot. So HRTEM is very important technique and it is a part of TEM technique, keep in mind. So atomic structure, properties of the material on atomic scale can be observed with the help of HRTEM. We have analytical electron microscopy where we do the elemental analysis in TEM like EDAX and EELS, electron energy loss technology. So this is in TEM. So this also are the different types of the TEM. Here I would like to show you the photographs from the book by Williams and Carter. First one, this one, is the JEM 1.25U mega electron high voltage electron microscope. So what you can see, this is the user and this is up to say 4 feet or so, and this is the electron column for generation of very high voltage. You can see the voltage tank is another room above the column. So this is a special purpose HVEM. We have this HRTEM, where the large frame forms the high mechanical, provides the high mechanical stability to the column. And these are our routine TEM, Hitachi made 200 keV S10, and this is JEOL Japan made 200 keV TEM or STM. And this is the model which we have ordered and which we have received in the Common Facility Center. 200 keV JEOL TEM. We have other Nikon model, we have FAI Titan model as well. Just for your information, I am giving you the images. So what kind of study can be undertaken so far as TEM is concerned? As I told, we can do the micro and nano analysis or micro and nanospace analysis based upon the visualization of the specimen with the help of electrons. Detailed microstructure at high resolution is possible. We can study crystal structure, we can see orientation, we can see chemical composition, we can study diffraction pattern, and we can do electron energy analysis. What kind of samples? Almost all types of samples ranging from metals, alloys, ceramic, glasses, polymers, semiconductors, composites, and other materials. They can be studied with the help of TEM. Nanostructures, one-dimensional, zero-dimensional, two-dimensional, three-dimensional nanostructures, they can be studied, they are studied with the help of TEM technique. And not only material scientists, the biologist also can use in microbiology, in forensic studies, TEM is extensively used. To study stale structures and bacteria and viruses, fungi, the TEM is useful. And this is very well known teardrop model of the electron interaction with the matter. So this is the electron beam, and electron beam interact with matter depending on the energy of the electron in the teardrop, three-dimensional teardrop type of volume, interaction volume. So depending on from where the signal is coming, whether it is secondary electron or OJ electron, or whether it is backscattered electrons, or whether it is X-rays. So different techniques are there, and I have discussed all these techniques in my previous lecture. But if the electrons, they transmit through a sample having thickness say 100 nanometer or so, then the technique is TEM, morphological information with the help of TEM. If the electrons which are transmitted, if they are elastically scattered, then HRTEM. And if they are inelastically scattered, then EELS. So all these aspects we are going to cover in my today's lecture. If we see the working principle of TEM, it is very similar to that of slide projector. Those who have seen the slide projector, prior to LCD projector, there were slide projectors, and we used to put the slides between the light source and the screen, and we get the magnified image. So for getting magnified image of the matter on the slide, you need a light source, and then condenser and objective lens. These are optical lenses, and the slide where the material to be projected is written or photographed, it's kept here, and we see on the projection screen the magnified image of the slide. Very similarly, slide is replaced by a specimen, very thin specimen, and these lenses they are replaced by the electromagnetic lenses, objective lens and core condenser lens. And importantly, light source is replaced by electron source, and we get very similar type of image, very similar to slide projector in TEM as well. So these are the two block diagrams. This left one is of scanning electron microscopy, and this right one is of transmission electron microscopy. So in this scanning electron microscopy, as we know, this is a gun, electron gun. This is condenser lens. This is probe forming lens, and we have objective and focus projector lens in TEM, but here it is not. When the electron beam is scanned over the sample surface, the various type of signal like secondary electron, backscattered electron, X-rays or specimen current or EBIC, etc. and they are recorded, they are amplified, they are analyzed, and the signal is given to cathode ray tube or the computer screen, and data is stored in case of SEM. But in case of TEM, the sample is thin and the electron beam get transmitted. So we need the another detector instead of secondary electron, backscattered electron or X-ray. We need another electron detector which is below the sample, and we need objective and projector lens as well. So the magnification in the TEM is the product of magnifications of condenser lens, probe forming lens, and the objective lens. So in this way, the magnification increases, and corresponding signal is projected on CRT, very similar to ACM. What are the various parts? Of course, we are not the instrumentation scientist, but just for sake of information, we need to know what are the various parts of the transmission electron TEM machine. And this is the actual photograph, and it's the cutaway diagram of the internal structure of the TEM. So we have electron gun, very important. Then we have electron column. Then electromagnetic lenses, as I told, three type of lenses are there: condenser, objective, and projector lenses are there. Water chilling system should be there. Detector should be there. Electron detector somewhere here. And if it is redox, then very near to sample, you need the X-ray detector. We have specimen chamber and image capture system. Total magnification, as I said, is the product of three magnification of the objective lens, then condenser lens, and the projector lens. And each is capable of magnifying say 100 times. So here itself 10 to the power of 6 magnification can be achieved with the help of these. What is magnification? Let me, because all our MSc students and other research students are there, let me spare some time in discussing what is the difference between magnification and resolution. And when we say magnification, 5 crore or 1 lakh, what exactly mean by this? So, magnification is just a ratio of two lengths. One length on our display unit, that is CRT or computer screen, and another length is the same scanning on the sample. So this magnification is defined by considering SEM, for example. So when this is the D is the length where we scan the electron beam for the distance D on the specimen, and we have correspondingly image formation having length D on the display unit, then the ratio of D and D, capital D and small d, is called as the magnification. In case of TEM, it is 5 crore, for example. And resolution. Resolution is not in terms of multiplying factor into x times x. No, it is length. So in order to find the resolution, we need to think of the important fact that the electrons, they are supposed as the waves, because according to de Broglie hypothesis, we know each, each particle exhibit a wave, and if they are electron, then the wavelength of a matter waves is lambda is equal to h by p. P is mass into velocity, where velocity is taken from the kinetic energy. 1 half mv square is equal to ev. From this v can be calculated and it is put there, and we get the simple relation for wavelength of electron, lambda is equal to h by p. Just by putting v, for example, say 1 here, 1 volt or 1 kV, because this relation is for k volt. kilovolt. So if I put V is equal to 1 kilovolt, then the wavelength of a matter waves exhibited by this electron is of the order of 1, and we know this wavelength is comparable to the interplanar spacing, and therefore these electrons having this much wavelength can be used to study the diffraction in case of a material. So based on wavelength, how to find the resolution? And it is given by Abbe equation, we know. Sorry. And the formula is D is equal to lambda upon numerical aperture. And numerical aperture in case of electron microscope, it is given by 2Na, where alpha, of course, this n sin alpha, A is n sin alpha. Therefore, by putting lambda from there and by putting voltage and etc., the D can be 0.7 divided by alpha V. Alpha is the half operating angle and V is the acceleration voltage. So, for 100 keV, for example, the resolution is 0.24 nanometer. Now you can put here say 1500 kV in case of high voltage, and therefore resolution increases. High voltage transmission electron microscopes are needed to increase the resolution. Here is the answer why resolution increases. Whether vacuum is needed in the electron column? The answer is yes, because we use electrons having very high energy. When the electron they travel in the column, they collide with the sample and they get transmitted. There should not be hindrance to the motion of these electrons. And we know the column where there is a air environment in the column, there are large number of gas molecules or the molecules in the gas space, and the electrons they are scattered. And when they are scattered by collision on these molecules, they lose their energy. And if they lose their energy, then it is very difficult to get the actual image or actual information in this study. And therefore, the ultra high vacuum, I am going to tell you the difference between high vacuum, medium vacuum, low vacuum, and ultra high vacuum, etc. Very high vacuum, etc. etc. So, ultra high vacuum is needed. Why it is needed? So, this is the range of low vacuum, vacuum of the order of say 1 to 100 torr, medium vacuum of the order of 10 to the power of minus 3, high vacuum of the order of up to 10 to the power of minus 6 torr, very high vacuum up to 10 to the power of minus 9, and ultra high vacuum which is better than 10 to the power of minus 9 torr. Why such a high vacuum is needed, and why in case of TEM we need to put 10 to the power of minus 7 torr or 10 to the power of minus 6 torr, etc., means 10 to the power of minus 9 bar or 10 to the power of minus 4 Pascal. Why? Here is the relation based upon the ideal gas equation, where mean free path, it is the average distance between two successive collisions of the electron. It is related to this rho by this relation, and this is very well known relation. In solid state physics we have already derived this relation, lambda is equal to 1 upon square root 2 pi d square rho. So if we just put this rho from there, and you get pressure is inversely proportional to mean free path. So if we increase pressure, then mean free path will increase. And why to increase mean free path? If we increase mean free path up to 1000 or so centimeter, of course, then this is the width of the column, and therefore the electrons will not come across the collisions and they will not lose their energy. So, for collision free conditions, pressure of the order of less than 10 to the power of minus 4 torr is needed for collision free. Okay, and for maintenance of a clean surface, the pressure of the order of 10 to the power of minus 9 torr or even less than that is needed. At various stages of the column, for example, this is a specimen holder, here it is electron gun, here it is viewing screen. At various parts, various pumps are used and various pressures or vacuums are needed. For example, here in the viewing screen, rotary pumps where few millibar vacuum is needed. Here, the turbomolecular pump or oil diffusion pump 10 to the power of minus 7 millibar, and ion getter pump, you get ultra high vacuum where specimen and electron gun are placed. So as I said, the sample electrons get transmitted through the sample, but we cannot keep the samples hanging, or you cannot just hold the sample with the help of some type of screw, or and then electrons are touched. So for holding electrons, a certain type of holder, specimen holder, is needed. It is called as mesh or grid. A common material used for preparing the mesh type of or grid, they are copper, molybdenum, gold, and platinum. Generally, these grid materials, they are covered with formover or carbon material, just to avoid reaction of the electrons with the grid material. So TM samples, they are supported on a mesh or grid. And here you can see, if you are able to see, those who are watching this lecture on computer, they may see here a whitish type of sample. Can anybody tell me, those who are seeing on computer, can they see this sample? White colored sample, this one?
Yes, sir.
Yes, you can see the sample. So this sample is kept on a mesh, and this sample is cut with the help of ultra micro term. This is a biological specimen, and these meshes, they are kept in this sample holder, and this is put in the electron column, and there is a airlock between this specimen stage and the ore column. Why? Because you see, if there is a vacuum inside the electron column, and if you want to insert a sample online, then the vacuum should not be ruptured. So for that, airlock is necessary. And this is the single axis tilt sample holder, a side entry in the TEM goniometer. And these are the various geometries of the sample holder. Electron gun, because the electron is the heart of this technology. The electron gun, they can be thermionic emission type of gun, or they can be field emission type of gun. If they are thermionic emission type of gun, then they follow the Richardson-Dushman equation, or they follow this equation where thermionic emission current density is given by J is equal to T square e to the power of minus 5 by kT. T is the temperature and phi is the work function of the material. And generally, the tungsten is used for the thermionic emission. Lab 6 also is used. But the way in which electrons are emitted in the thermionic emission, they are totally different than the way in which electrons are emitted in the FE source, field emission source. I have told in my previous lecture on EDAX that in our department of physics, there are two types of SEM. One is ordinary SEM and other is FESEM. This FESEM is a field emission scanning electron microscope. But in transmission electron microscope also, you need electron source. So it can be a thermionic type, or it can be field emission type. So what is the advantage of field emission type of electron gun? This is called as a cold source. Field emission is called as cold source because thermionic emission is the hot source, or the thermionic emission takes place at very high temperature of the order of 1000 K or so is needed for emission of the electron. So this is one of the disadvantage of the this electron and method, thermionic gun, and therefore the field emission gun are prepared, and field emission gun requires the very high fine tip, fine tungsten needle you can see in case of field emission, where the field is applied between the source and the cathode, and it is applied in two stages, first anode and we have second anode, and this is field emission, and very highly focused and highly direction electron beam can be achieved with the help of field emission gun. And these are lab 6 and tungsten are, these are the photographs which are available in the handout of the JVOL company. As I said, the optical lenses, they are replaced by the electromagnetic and electrostatic and magnetostatic lenses just to control the flow of electron or the motion of the electron, the size of the electron beam, because it is not this one electron by other electron they are coming. The electrons they are coming as a beam. So we have a cross section, the diameter cross section, where we can see the electrons crossing per unit area per unit time, and therefore this electron beam current or the beam should be controlled, monitored with the help of a kind of mechanism. In case of optics, electromagnetic radiation, they can be controlled with the help of the optical lenses. Here, with the help of electromagnetic lenses, where the electron motion can be controlled by applying changing electric and magnetic field to the lenses. So these lenses they are used to focus the parallel electron, the constant focal distance, and they can be operated electrostatically and magnetically or electrostatically. And majority use of electromagnetic coils to generate the convex type of lenses. We know there are two types of convex and concave. Convex means focusing, is it not? So radially symmetrical fields are applied to avoid aberration. Aberration, these are the terms from the optics, and astigmatation also the terms are. And this is out of scope of my lecture to explain what is meant by aberration and astigmatation. Generally, the materials like iron or the alloys of iron and cobalt and nickel and cobalt, permalloy, they are used for formation of these electron lenses. You need detectors in TEM as well. Very similarly, in case of SEM, you need a detector. Particularly, semiconductor detectors are used in case of EDAX, energy dispersion analysis by X-rays. WDS and EDS I have explained in my previous lectures. So we need two types of detectors. One is the electron detector, which is below the sample, and it can be scintillation detector or other type of electron detector. But you need say radiation detector, for example, in case of energy dispersion analysis by X-ray. So semiconductor detector is a primary choice, important choice, and generally these are used where X-ray energy dispersive spectroscopy EDS or EDX system, where it contains the large divar of liquid nitrogen 2. This is kept for the detector cold solid state detectors, particularly silicon type of detector. When a particular X-ray they fall on semiconductor, the electron and hole pair are generated. And depending on energy of the absorbed X-rays, the energy or the current electron hole pair they are generated, the pulse height is proportional to the energy of the X-ray absorbed. So the X-ray absorbed X-ray can be conveniently what you can say distinguished, identified, categorized. So electron detectors are the or the detectors in the energy dispersion analysis. They are solid state detectors, silicon detectors. Apertures plays a major role in various modes of operation of the TEM. These apertures are, as you can see at the bottom of the slide, aperture strip is shown where various aperture, annual metallic plates, annular metallic holes you can see. These are apertures, and this is a metallic plate, and this is aperture holder, very similar to sample holder. We have aperture holder now, and these apertures they are kept in the path of the electron, and where these aperture strips are kept, that decides the mode of operation of the TEM, and these can be moved in or moved out, and appropriate aperture can be chosen, is it not? So these aperture they permit the motion of axial electrons. Either they are used to decrease the beam intensity of the electron or to remove the scattered electrons. Only fine beam of the electrons are can be focused, can be allowed to what you can say fall on the sample. For selected area electron diffraction side, these apertures they play a very important role, and the aperture strips they are used prepared with the help of the kind of metal molybdenum, and we have different size of apertures, very important. I'm going to explain you by taking simple example of two type of imaging modes. One is imaging mode, which is shown here on the left hand side, where we take image in the TEM, and this one is the diffraction mode, where we study the electron diffraction. So in the same instrument, we have SAD pattern, we have imaging mode, we have STEM, we have HRTEM, and so many other things. And here you can see just the position of the uh, that aperture, where this objective aperture, if it is in the back focal plane of the objective lens, back focal plane of the objective lens. Here is the focus, this is the back focal plane. And when this objective aperture, if it is in the image plane of the lens, this image plane, this is image plane, real image plane of the lens, there you get the diffraction. Means the pattern what you observe is the diffraction pattern. So you see the position of aperture itself. Of course, here objective and other projector lenses, screen, sample, etc. they are shown. But important thing is the position of the objective aperture. In the back focal plane, you get imaging, and in the plane of objective lens, means here, for example, here and there, you get the diffraction pattern. So if you see the cross section of the electron beam which is coming out of the sample, so we have transmitted beam with the help of imaging mode, and we have diffracted beam which comes due to this damage geometry, and you get the spots. I'm going to tell you how you get the spots in the diffraction mode. So the beam or the cross section of what you can say, the geometry below the sample, it contains the transmitted beam and the diffracted beam. So what you choose will decide what kind of picture you are taking. So if you select the transmitted beam in the objective aperture, for example, then we get the bright field image, or it is a bright field method. Now, if you select with the help of objective aperture, if you keep your objective aperture such that only diffracted beams are allowed, then it is a dark field method. So this is dark field method, and this is the bright field method. Now, if both are simultaneously focused, then it is called as HRTEM. And I am going to explain. I am going to take your time on this high resolution transmission electron microscopy at the later part of my lecture. So, where your objective aperture is, whether it is in the back side or in the first image plane, then there the bright field image or sad pattern or dark field image or the direct field image on other side is formed. So this is the photograph, transmission electron micrograph of ZNO crystal, and it is the bright field. What you see, field is bright and image is dark. And here this is dark field, means field is, background field is dark and image is bright. So you can just distinguish between the photographs and images, and you can characterize. You know more about the, and these are the TEM images taken in dark field, and this is bright field. You just see the difference between the photographs, and a lot of information is hidden in bright field and dark field images. So you can see the basic difference between the scanning electron microscopy and transmission electron microscopy images. Sorry. So the basic difference between SEM and TEM is that in TEM, most of the microspheres have single hole. Here you can see single hole, you can see in the SEM, but in TEM what you can see, this hole also has got structure, and you can see holes which are below or backside of the atoms, backside of the, what you can say, the microspheres. These are the typical transmission electron micrographs of the oxide nanomaterials. You can see this bar is 20 nanometer, this is 200 nanometer, this is 20 nanometer, this is 50 nanometer, and all these are the TEM images, and these are published in this reference. These are the transmission electron micrographs of taken for the biological samples. Particularly, these are TEMs of poliovirus, and these are TEM of S. aureus, one of the bacteria. This is COVID-2, COVID-19, SARS virus. These are the photographs. Somebody will say, how come the color came? So you have the choice in your recording device, or in your, what you can say, computer program. You create a computer program, you in a such a way that this computer program recognizes element, for example, from EDAX technique or EELS technique, and you get a different color for the different things, and therefore colored image are created. These are not directly seen, keep in mind. Even in case of SEM, I have shown in my previous lecture colored images. So it is not the artifact of your instrument, it is the artifact of your program. So this was about the TM image formation. Now we proceed further to look at the another dimension of this technique, diffraction. As I said, these electrons, if they are accelerated at very high voltage, for example 100 keV, then, or 1 keV for example, then the effective diffractive wavelength is of the order of 1 nanometer or so, and this wavelength is comparable to the interplanar spacing, and therefore these electrons, which have dual nature, they have particle nature and they have wave nature. Wave nature of these electrons can be utilized to study the diffraction of very thin samples. You see, X-ray diffraction has got its own disadvantage, that if they are thinner samples, then X-ray diffraction peak intensity is very, very small, and we cannot really analyze, characterize the crystalline structure of the material in a correct way. But if it is electron diffraction, for example, in TEM, then even though sample thickness is very, very small, we can do it. And you can tell whether the material is polycrystalline, single crystalline, or nanocrystalline, or amorphous, even just by looking at the diffraction pattern in TEM. So, wave nature of the electrons, where the shorter wavelength is utilized and the electrons are scattered strongly, and the beams are easily directed. You can tell whether material is crystalline or amorphous. You can tell the crystallographic characterization of the specimen, whether you can material is polycrystalline or monocrystalline, single crystalline. This information also is obtained with the help of diffraction in the TEM. Grain morphology, grain size distribution, phase presentation, orientation, so many things we can be learned in the diffraction. And on what principle it is based? Let us see. You can suppose your sample as a mesh, just a mesh, net, is it not? Net for what? For the electron beam. Because the interplanar spacing and the wavelength of the electron size, of course, is very, very small, but the wavelength of the electron, it is so small comparable to the interplanar spacing that they just pass through it. But they do not just pass through it, they get diffracted according to the 2d sin theta is equal to n lambda, Bragg's law. So lambda is equal to h by p, we know, and this I told, if we put for voltage to be 1, for example, lambda is equal to 1.23 nanometer. And if D is equal to 2.5 angstrom, for example, then the wavelength is very, very small. You can say at 200 keV. And diffraction angle you can see 0.0. It is negligible. Diffraction angle is negligible, means you just talk in terms of the wavelength of electrons, then interplanar spacing based on other measurements, not on theta. So this is incident beam gets interacted with your crystal plane, And this is transmitted beam and these are diffracted beam, and this is the angle between incident and diffracted beam, and this angle is very very small. That's what I want to tell. Information about the crystalline structure can be obtained when we study the electron diffraction. So crystal lattice acts as a diffraction grating, as I told, and for diffraction grating we know when the electromagnetic radiation, the incident on the grating, then we get wavelets, and there is a interference. So this interference, when it is projected, it forms an image, and we get a regular dots and rings. Why we get regular rings or circular type of pattern, that also I am going to tell you in the next slide. But the diffraction pattern, if it is diffuse type of rings, then your sample is amorphous in nature. So no dots, no rings, no circles, diffuse type of pattern, then it is amorphous. And if you get the bright spots, circular bright spots, then it is crystalline. If the bright spots, they are densely arranged on the circular radius, then it is polycrystalline. So small spots making of rings. And if the spot size is small and density is high, the polycrystalline material is no more polycrystalline, it is nanocrystalline. So ring pattern is observed if in the electron diffraction, if your material is nanocrystalline. You get small spots, polycrystalline. You get bright spots, distinct, then crystalline, etc. Kikuchi pattern also is a kind of thing in TEM where mapping is possible, and inelastic electron scattering is studied with the help of Kikuchi pattern. But this requires another lecture also, and I'm not going to explain. For us, this is important. What kind of pattern we get for our material? So depending on position, as I told, our this one should be in the back focal plane and image plane, where when you put your aperture at right position, you get SAD pattern. Selected area electron diffraction, SAAD. So I will tell you what do you mean by what is the long form. Electron diffraction, ED is there. Selected area. So you select the area with the help of your aperture, with the help of condenser or the focusing lens also, and there you get the pattern, and therefore it is called a selected area electron diffraction. So again, this is the back focal plane, and this is the image plane. Depending on the aperture position, you get the electron diffraction. So this is the back focal plane. This is the back focal plane. This is your sample. Electron beam is incident on this, and you get transmitted beam and you get diffracted beam. And diffracted beam, they are collected when you keep your aperture in the back focal plane, and you get the diffracted spots and transmitted spots. For understanding how we get spots and how we get circular spots, we just touch to the crystallography and few aspects from the solid state physics. One is the reciprocal lattice. I would like to tell you, when we say lattice and when we say reciprocal lattice, a lattice is the regular periodic arrangement of the atoms in 3 dimension we know. For example, let us say A1, A2 and A3 are the radius vectors, or what you can say uh, vector directions for the 3 directions of the lattice. And B bar is such that it is along the direction where the cross product of A2 and A3 is there. A2, A2, A2 and A3. Of course, I have made a mistake here. This is A2 and this should be A3. This should be A1. No, sorry, it is correct. B3. B3 is perpendicular to A1 and A2. So it is correct. B3 is perpendicular to A1 and A2. So when we define B1, B2 and B3 and form another lattice out of these vectors, new vectors, then a reciprocal lattice is formed because the B3 is magnitude wise proportional to 1 upon D001, for example. So the radius vector of the reciprocal lattice, they are reciprocal of the interference spacing, and therefore the name reciprocal lattice. And we know diffraction occurs in the reciprocal space. Keep in mind. Another concept called as EVAD construction. The students who were having solid state physics specialization in physical properties of matter, this EVAD construction is there. Even in solid state physics, this EVAD construction is there. What after all this EVAD construction is, I am going to tell you. This is our Bragg's law. 2d sin theta is equal to n lambda. This law is written for sin theta is equal to, it can be rearranged lambda by 2 and d, and this again can be written lambda by 2 can be taken below and 2 by lambda can be written, and this d can be taken in the numerator and 1 upon d can be written. So sin theta is equal to 1 upon d divided by 2 by lambda. So in this Bragg's equation in the reciprocal space, this is called as Bragg's equation in the reciprocal space. So here we have crystal related information in the reciprocal lattice. And here 2 by lambda means radiation related information in the EVAD space. So you see in the Bragg's equation in the reciprocal space, the crystal related information and radiation related information is there. This radiation is from electron and this is from your crystal. So this is the direction of incident electron wave, for example, and it is given by a momentum vector k bar. And after diffraction, let us say it goes to k bar, and 2 theta is the angle between incident and diffracted direction. Then the EVALD, he defines k in a such a way that it is 2 pi by lambda, and circular circle is drawn. Wherever this circle intersects, there you get the spots. That's what the EVALD sphere touches the reciprocal lattice. Bragg's equation is satisfied at those positions. Is it not? And therefore, this EVALD sphere construction is important in formation of spots. And this image I have taken from Lave diffraction because the incident radiation is X-ray. Instead of X-ray, now we have electrons here, but very similar type of this is the reciprocal lattice, and we know at only important locations the Bragg's condition is satisfied, and there only X-rays are allowed to form what you can say interfere. Similarly, the electrons, they form the spotty pattern in 2D projection. Is it not? So how to index a diffraction pattern, electron diffraction pattern? This is incident electron beam. This is EVALD sphere, for example, and this is thin sample, and this is our non-diffracted beam, and this is diffracted beam. This is 2 theta is the angle between them, and this is the L. L is the distance between crystal and your detector, and R is the radius of your diffraction pattern ring. And then from the simple geometry, you can see sine theta. This is 2 theta. So sine 2 theta is R by L, and L can be written as R by 2 theta because this 2 theta is very small, 0.1 of the order of 0.1 or so. Therefore, if theta itself is very small, sine theta is equal to theta, we know. And similarly, here also L is equal to R by 2 theta. Now, this 2d sine theta is equal to n lambda also can be written because sine theta is equal to theta and n can be 1, and therefore 2d theta is equal to lambda. So, if you equate these two and get the relation, you get d is equal to lambda L by R. So, interplane spacing is equal to lambda L by R. What is L? You know the distance between your crystal or the sample and the detector. So, that is known. Or from the diffraction pattern, you can measure the distance between the middle spot and the spot, first ring, second ring, etc. So you keep in mind, for each plane, you get one ring. This is the reason why you get the ring pattern, because the sample or the beam is Ewald sphere is formed in the two-dimensional plane, and therefore you know lambda from the acceleration voltage, you know L, you know R, you can find D. And this is the simple way. Just by knowledge of D, you can index it and you can study the diffraction. Depending on your lattice parameter, if the lattice parameter is large, then density of your spot this is the same view plane, same dimensions, length and breadth. So if A is greater, the density is more. If A is less, density is less. So this was about the diffraction in the TEM. Hope you have understood. Of course, it is not so easy to digest in one attempt. But as you know, I am recording this lecture and I am going to put this on YouTube channel. Therefore, you can once again visit that and you can refer the book which I have given and you can know more about the diffraction. But it is a very important and very crucial study as far as material characterization is concerned, nanomaterial characterization is concerned. If we combine TEM and ACM, then it forms the HTEM, and it is based upon the reciprocity theorem. What reciprocity theorem says? Here it is source, here these are lenses, this is sample, and this is detector. So source and detector, when source is replaced by detector and vice versa, means here detector is there and here it is source. So what do you mean by this? I mean by this, when electron is passes through sample and it hits the detector, and once again this electron, it is being detected by the position observer sitting at source, then it is called as STEM, it is called as reciprocity theorem. Therefore, objective lens aperture, if it is kept below the objective lens, for example, then image detector. And in S10, what you need? You need focused beam. You need focused beam. And you need the raster scanning on the sample. Then only, if the beam is not focused, then this will not act as a point source. Keep in mind. And therefore, you need focused beam. So, in conventional transmission electron microscopy, the beam is not focused. While in case of STM, the beam is highly focused and the spot size is of the order of not 5 to 0.2 nanometer, and which is scanned over the sample in the raster way. And sample is illuminated at each point, and rastering gives you the Z contrast, annular DF imaging. What is the DF imaging? I am going to tell you. And spectroscopic imaging like energy dispersion analysis by X-ray or uh, electron energy loss spectroscopy. So, chemical analysis in TEM is done with the help of S10. Keep in mind. You see, this is the annual dark field image and annular bright field image for the same sample. Keep in mind, for the same sample, but in the S10 mode. What you can see? You can see the atoms, say strontium green atoms and O red atom. Then this is the SRTIO and other RTI. These are gray RTI. So this is possible with the help of S10. Also, the spiral structure of FeAl alloy, where the spiral structure is ferromagnetic region and surrounding black is the non-magnetic region. So such kind of study is possible, feasible with the help of STEM in addition to taking only pictures of the sample. If the electrons which are transmitted, this was about the STEM. Only two slides I prepared as far as this is one dimensions of the transmission electron microscopy, STEM. After STEM, we have EELS. Of course, we have one more dimension, that is one more aspect of this TEM, that is HRTEM. Please be patient. another half an hour and my lecture will be over. I have already taken 1 hour and 15 minutes. Still half hour is needed to explain the HRTM at length. So this is another aspect of the transmission electron microscopy called as electron energy loss spectroscopy. And this, with the help of electron energy loss spectroscopy, we can know about the valence of the material. We can know the bond length. We can know the nearest neighbor coordination. We can quantify the atomic species in the minerals, means chemical analysis. So many parameters which are needed for ritual refinement. Those who have heard my lecture of ritual refinement, many input parameters are needed. Particularly bond length is needed. The environment near the atomic position is needed. Debye factor is needed. Such kind of parameters, they can be found with the help of EELS. So here, transmitted electron, they lose energy. This is very important aspect. When the electron, it transmits through the sample, some energy is gained by the atoms or the electron in the sample. But this energy is being lost in the beam. And if we record that lost energy, then that would be a very important aspect for material characterization. And we can theoretically calculate the desired energy loss. So in the EELS spectrum, we get the photon excitation, we get inner or intraband transition, we get plasmon excitation, and we get inertial ionization. So EELS spectrum contains the photon excitement, we get intraband transition, and we get plasmon excitation and inertial ionization also. So this is the typical EELS graph. So experimental EELS spectrum shows major features like zero loss peak. This is due to elastically scattered electrons, as I told. We get plasmon peaks. This is due to valence electrons and plasmons. I will not define what the plasmon means. And we have the peaks due to core loss edges. And these core loss edges, they are due to electron characteristic element. These are due to element. And therefore, oxygen, manganese, and lanthanum in LASRMNO is seen here within 500 to 900 electron volt energy loss. So this is defined as a high loss, core electrons, and this is low loss, valence electron. It is possible to study the environment of the atoms. For example, if titanium is in Ti2O3, then peak positions are somewhere here. If it is in TiO2, we have different 4 peaks and positions is different. And in CaTiO3, peak position. So it is possible to locate the valence state of the Ti. So Ti3 plus, Ti4 plus, Ti4 plus with the help of EELs. Even twist boundary is not. In this age from the twist boundary can be studied in TiO2. In the electron diffraction, seabed, convergent beam electron diffraction is one of the, in STEM it is there. So in STEM we know the electron beam is highly focused, and if the electron beam is highly focused, then the SAD pattern, instead of spots, we get the disc-like of pattern. And this disc-like of diffraction disk, it includes very great information like atomic coordinates, Debye factor, etc., etc. Thickness, specimen thickness can be calculated, lattice parameters can be calculated, many things can be calculated, rocking curves. So seabed pattern is in a part of STEM. Actually, I misplaced this slide. This should have been in STEM. And then it came the EELS. And last aspect of my lecture is high resolution transmission electron microscopy. When I say high resolution transmission electron microscopy, I mean by high energy resolution, high, let me go to that slide, and once again I will come to this slide. high spatial resolution, high energy resolution, and high chemical resolution. Spatial means high spatial frequencies. High means you see time in time domain 1 upon t is frequency. In space domain 1 upon x is a frequency. So Fourier transform, the time is converted, or the spatial parameter is converted into frequency parameter with the help of such. So when I say high resolution, high spatial resolution, high energy resolution, and high chemical resolution. High chemical means we need to detect small quantities given chemical species. We need to resolve closely positioned energy levels. So such type of aspects we talk in terms of in high resolution transmission, and this is used in imaging and diffraction modes. This is a picture of transmission electron microgram, or it is a TEM image, and this is HRTEM image. You see, scale bar has changed from 50 nanometer to 5 nanometer, and this is corresponding SAD pattern. This is image, this is high resolution transmission electron image corresponding SAD pattern. Here itself you can see, if your TEM is not HRTEM, then a very useful information, you are away from very great useful information. With the help of high resolution phase contrast image, you can just see this is grain number 1, where interplane spacing is different, and this is grain number 2, interplane spacing is different. And you see, this is the formation of intergranular glossy film, IGF. So this such kind of observation, such kind of study is possible with the help of HRTEM. In HRTEM, as I said, spatial magnification means if we just magnify, you know, in our mobile camera also, we just magnify image, and image is if magnified, then blurred image occurs. So similar thing takes place in TEM also. If you just go on increasing the magnification, the blurriness will increase because information will be same, and you are just magnifying the image. So useful information is necessary in HRTEM. This is not allowed, or this is not expected. Something different is expected. What is expected? You increase resolution, as I told in this formula, d is equal to lambda by 2. So if we increase acceleration voltage, the resolution increase. So with the help of electron source, resolution can be increased. So this is the picture of fully resolved images, and this is just resolved, and this is unresolved. So we wish to go from this unresolved phase to fully resolved by choosing the electron source where the potential difference is chosen, or by imaging system. So by increasing electron acceleration voltage, or by choosing imaging system, lenses and apertures in such a way that the resolution is increased. How? If we, for so far as lenses are, electromagnetic lenses are concerned, so these are the parameters: spherical aberration, chromatic aberration, astigmation. These are the optical terms, and we will not go in the details of the. But in HRTEM, the parameters like CS, spherical aberration factor, then delta F defocus parameter in the astigmation. So these are the things which we are going to take ahead in the discussion in the next slide. As far as apertures are concerned, with the help of apertures also resolution can be increased. So dark field image, or whether it is a bright field image, or whether it is a shade pattern, or it is image contrast, etc., etc. So with the help of aperture control, resolution can be increased. With the help of choosing electron source, the resolution can be increased. With the help of choosing the parameters of the lenses like CS or delta E or beta or delta F, the resolution can be increased. Keep in mind. So how to increase the contrast? What do you mean by contrast? This is less contrast image, and this is high contrast image. So far as contrast is concerned, image formation in HRTEM relies on the phase contrast. So amplitude contrast is the absorption constant and diffraction contrast. This is a small effect in the thin film samples. But in HRTEM, phase contrast, where the formation of fringes due to thickness, bend, Fresnel, Murray, and lattice. So these phase contrast, if you want to increase the contrast, then phase control. But we are going to talk upon HR, high resolution. So we will talk little about the contrast, but we will talk about the resolution in depth. So for that, we need to study some mathematical concepts, particularly Fourier transform. So we change from spatial discussion to frequency, where we change from spatial domain to frequency domain in Fourier transform, we know. And Fourier transform, the signal in Fourier transform can be written as sum of many sine waves. So these are the two things we will understand first before discussing the role of optical system in HRTEM is concerned. So microscope transforms each point on specimen into extended region in the final image. Is it not? A small point of the object is seen like this disk because it is a two-dimensional imaging. So you suppose it as a extended region circle in the final image. And how it is done? Hello? Hello? आवाज येतोय का सगळ्यांना? अमित?
Yes, sir. Yes, sir. Hi, okay, sir.
Okay. Only another 15 minutes. I will cut short my discussion because it seems you got tired of this heavy dose. But I will cut short my discussion anyway. So if a point on specimen, if it is described by a point function f of r or f of xy in real space, then in reciprocal space, this point we need to think of reciprocal lattice, is it not? This is simple lattice, this is reciprocal lattice. So here also point, here also point. But when you increase resolution, high resolution you need a point spread function. This f of r is increased or spread by function hr to get g, where g is the image in or magnified image, you can say, or high resolution image, for example, in real space. But keep in mind, when we use SAD pattern or when we use a transmission electron microscopy, we need to think of the Fourier transform of these f. Fourier transform of f is f of u, h it is hu, it is called as contrast transfer function, and for g we have capital G. And this capital G, this small g could be this convolution of f and r. Convolution means integration of product. Convolution means integration of the product. So this is the Fourier transform in 2D, sum of all sine waves, as I told. And image processing tools, they need the spatial to frequency domain, and each point has got a particular frequency. Therefore, if it has got particular frequency, then the frequency is defined by u in the reciprocal lattice. So g is equal to g times e to the power of 2 pi I u. So Fourier transform of g is image, is it not? It is represented by this g. G is equal to h times f. So if you take 2 points, one A and B, in real image or sample, they form the extended rings in the what you can say, in the two discs in the image. But we don't know whether this part of the image is from this point or that point. And this issue is being resolved in HRT. Are you understanding what I say? You see, this point is magnified by this disc and this point is magnified by this. But what we see actually in the TEM is this, for example, but we don't know this part is whether from B or whether from A. So for that, this point spread function and G is defined as the specimen transmission function multiplied and integrated, that is called as convoluted in real space, is replaced by the product in the multiplication in the reciprocal space. So for this G, this capital G, for this F, this H, for this H, this is F. Now this H is very important. It is called as contrast transfer function. It is the product of aperture function. It depends on aperture. It depends on envelope function. It depends on aberration, means lens. This is lens. this is aperture, etc., etc. You see, when you choose a particular lens, then this aberration function or the aperture function, if you choose a particular aperture, if you choose a particular envelope, these two would be fixed. But the aberration function, where we apply electric and magnetic field for the lens, the light spreading effect is very important. This B is very important. And this B is given by e to the power of I psi u. This is called as phase distortion function. Later on, you will come to know it is function of delta f, which is defocus parameter, which is our choice. This is lambda, wavelength of electron, which is equal to h by p. From there it comes. And this is u is the reciprocal lattice vector because it is 1 upon d. U is equal to 1 upon d. Spatial frequency. And Cs is the spherical aberration coefficient. So, chi depends on these parameters, and these parameters controls chi controls b, and b defines h. Means final image in the HRTEM is controlled by defocus parameter, wavelength, reciprocal lattice vector, and spherical aberration. So we will think of discussing this at length in the later part. So let us assume a model, because for getting B for example, B is given by, so for example, this B is given by e to the power of I chi, it is given by sine. So for that we consider a model. A point function is defined by its amplitude times the phase factor e to the power of, a point is defined by uh, uh, amplitude, which is function of position coordinate, and into e to the power of minus 5. Phi is the phase factor. Why phase factor comes here, I will tell you. You see, when electron it transmits through the sample, then this electron will see the potential of the atoms and electron present in the sample. So ultimately, the electron which is transmitting through the sample, it will see a potential. It has to cross the potential, is it not? And this potential crossing will lead to change in the phase of the electron, because electron it exhibits the wave nature. So this change in phase, if somehow account, then it is possible to input or put in the formula for G. Therefore, so if we do first approximation, phase object approximation, where we put A is equal to 1, then it becomes e to the power of minus 5. Now this phase change, as I said, it is controlled by the voltage. The voltage is specimen potential is V, and if you just add all the voltages throughout the thickness, then it becomes Vt. It is called as projected potential, and this Vt would be integration of this V. Vt would be integration of this V, and this total phi change would be what, integration of this d phi. And how this d phi is calculated? D phi is equal to pi by lambda e Vt. Vt is integration of this one and sigma Vt, and this sigma Vt it appears there for this phi e to the power of my sigma Vt. Phi is equal to sigma Vt. And when we do another approximation, it is called as weak phase object approximation, where Vt is less than 1, then e to the power of minus x is equal to 1 minus x minus up, and all terms are neglected. And so we get 1 minus this, so 1 minus I sigma Vt. So this is F. Now this d phi, how d phi sigma Vt I got? Lambda is equal to h upon 2 pi mev. So for E, I need to consider the potential which is of the sample. So correction in E. So we have, when we are in vacuum, let us lambda is the wavelength of the electron. But when electron passes through specimen, it modifies its wavelength, and this modification is considered by potential. So this change in wavelength is accounted to change in phase 2 pi by lambda dz. So if we put these two and do simplification, we get this, and we get sigma Vt, and you can see the details in this book. So once again we apply this approximation in TEM, weak phase object approximation, where H was defined as A times E times B, and B was e to the power of I sigma u. So G is equal to F times convoluted H. So h is, say, let us say, take h to be cos plus I sine. It's a simple function, because we know in the Fourier transform any signal can be written as sum of all sines and cosines, and therefore such kind of function is defined, exponential function e to the power of minus I, etc. So cos plus I sine is h, and this one just now f is defined by that. And if you take this multiplication, define some function psi is a wave function as seen in the image. If we take complex conjugate psi star and take multiplication, it will give you intensity. That's what we are expecting, is it not? This is the intensity of the image, or intensity of the image, and therefore you see a parameter like 1 plus 2 I sigma Vt into sine. So B is equal to 2 sine xi, the only imaginary part which contributes to B, and therefore B is equal to 2 sine xi. This B is equal to 2 sine xi. Okay, so keep in mind, instead of exponential function, I replaced it by 2 sine. This 2 has come due to complex conjugate multiplication. Keep in mind. And therefore, the objective lens transfer function is equal to T is equal to A U 2 sine. Now, if we put this U another approximation, U is equal to 1, A is equal to 1, only 2 sine, this will be there. So, best way to appreciate the importance of xi, is it not? Because this is equal to 2, T is equal to 2 sine xi, is it not? Chi, they say, I define this is chi. So simulate, because chi is given by this pi delta f lambda u square cs lambda u. So for various lambdas means you have to tune the potential. So we cannot we cannot vary potential. You just keep one potential. So lambda is fixed, pi is constant. Then u is the parameter of your unit cell, or what you can say lattice. So that also can be changed. So what are the parameters? Parameters are delta f and cs. So we choose these two. For example, and potential is fixed, cs is fixed. So what we see, t starts from 0, it increases, goes maxima minima, and again comes to 0, and then comes ups and down. So when t is equal to 0, what do you mean by t is equal to 0? Means there is no image formation, because this t is b, means it is h, is it not? So when t is equal to 0, no image. So wherever 0 is there, there is no image. When t is negative, atoms are brighter, and when t is positive, atoms are darker. So depending on value of t, whether it is positive or negative, the atoms get brighter or darker. The intensity will increase, will decided by the value of t. So we will not think of any other value of the t, only values of t at maxima, at minima, at maxima. But we will select this region where t is maximum. So for this CS, for this E0, and for this delta F, the value of U, this one, value of U in nanometer, that will give you high resolved image. So fix CS, fix lambda, fix delta F, fix E0. So Switzer, they defined the defocus parameter and damping function. Why they used that? Because they want to remove this. Therefore, only they want to work there, and they want to choose this for example. So by this also is out of in the it will be out of scope of my lecture. So Caesar, they chosen the defocus parameter, damping parameter in such a way that the instrument they chosen this parameter, they are within the instrumental resolution level, and information ends there. So T is modified by the damping envelope. So when in your TEM, when you want to use the HRTEM feature, what you need to do? You need to choose the particular potential. You need to choose such a lens, or the applied electric and magnetic field for the lens, such that this parameter should be 2.2, for example, or defocus parameter in case of aberration avoiding. So this parameter. So choose these parameters and you will get high resolved the images. This is the HRTM images of multi-volt nanotube. Multi-volt nanotube. You can see these are 2 volts. These are 1, 2. So many volts are there. You can see 5 volts are there. And this is HRTM image of ZrO2 nano twins. If you carefully look at this image, add these twin planes, they occur. So such kind of study can be done. 5 volt, 2 volt, 7 volt nanotubes can be seen with the help of HRTM. Even in case of a single sample, if there is a hexagonal phase, if there is a cubic phase, this also can be distinguished with the help of HRTM. And this is another HRTM image of multi-volt carbon nanotube. This is also chemically modified carbon nanotube. Just I have gathered some pictures for your information. What can be studied. This is SEM image of TI-doped CEO2. This is TEM image of CEO2, and this is molecular dynamics based upon the HRTEM. So such kind of study is possible with the help of HRTEM. And this is the last slide of my presentation. What are limitations of the TEM? First one is we cannot take the colored image. Colored image means directly we cannot see, but we can create colored image with the help of some program. Thick samples beyond 200 nanometer, you need high voltage TEMs. A standard TEM cannot image surface information because surface information, for knowing surface, you need another technique like SEM or OG electron spectroscopy, etc. etc. Constant input voltage is necessary for TEM. This is one of the disadvantages. Preparation of the sample is tedious in TEM. TEM cannot rely on image charged molecules that are mobile in the matrix, and they are extremely sensitive to the vibrations and electromagnetic movements. So owing to some limitations of the TEM, this is a very nice technique, and soon in our common facility center, this technique will be installed, because this instrument have arrived, but due to this COVID pandemic, uh, it was not possible for us to install it the in time, but soon we'll be installing it. May I request our student friends to ask few questions related to TEM. If they can unmute themselves and ask the question. And if it is not possible, then you can type the question and Amit can ask the question which are in typed box or in the chat box. So all are requested to participate in the interactive type of discussion. Hope I was able to convey what I have prepared. Actually, this lecture was prepared 2 months back, before I was quarantined. So once again I have to prepare, and I went through all slides, and as time, I thought at the end while discussing HRTEM, it was not possible for me to take your too much time, and therefore I ran through the slides. So any questions? मला क्वेश्चन नसतील, प्रश्न विचारायच्या अगोदर, लेक्चर संपायच्या अगोदर विद्यार्थी कसे काय लिहू व्हायला लागले? कंटाळा आला, गाईडने बोलवले काय? Okay, anyway, if there are no questions, I take this opportunity to thank all the students and I'm going to put this lecture on my YouTube channel. Thank you very much for your time.